1 second. Okay.
Fritz, maybe you could show an overview of your slides. You know, you could just put up a slide sorter view, just like the big picture of your whole talk, and people could ask very specific questions about particular things that you talked about, or in general make some comment.
I can let me first.
Can you go to the slide sorter view?
Yeah.
And zoom it out so you see everything. Okay, yeah, there you go. So we'll just ask on Slack now. Let me try to get the Slack here. In general about the, by the way, just to get things going here, do you know John Hopfield actually attended the first couple of days here of the workshop?
That's amazing.
John Hopfield, yeah, who I believe was responsible for starting the second wave of neural networks, right? Because at that time, you know, at that phase, right, it was just after the perceptron and the Rosenblatt, you know, thing where people, I mean, thought that neural networks couldn't do stuff. And then John Hopfield came and wrote these two beautiful papers. I mean, they were really beautiful papers. Anybody could read them with physics background and just understand what was going on, because everything was posed in a very beautiful, you know, Lyapunov function framework. And at least being at Caltech at that time really opened my eyes. And I remember going over to John Hoffield's lab as a very naive young PhD student, physics trained, and finding a postdoc there and asking, you know, oh, what's going on, you know, in the lab here? He says, oh, do you want to ask about the electron transport, or are you interested in neural networks? I was like, what's electron transport? I didn't even know what electron transport is. He said, I want to hear about the neural networks, you know. So he got me really excited about this stuff. And so it's very nice that you mentioned this Hopfield work. And I wasn't aware even that the phaser networks came around, you know, just about 5 years later, right?
Yeah.
So now they've come back around again because time is still an element of this. And I'm sure many people here are aware that Hopfield again went back to the time domain when he was working on an olfactory system. He did this very interesting work on olfaction and the sniffing behavior.
Yeah, there was actually this time in the early 90s when also Andreas Hertz was at Caltech. And at that time, they wrote a few papers which are absolutely, well, very inspirational to us actually, which are about kind of doing these Hopfield nets with spike timing patterns.
Right, but the impact of John Hoffield's work was, unfortunately, the physicists started getting consumed, you know, obsessed with computing the memory capacity of these Hopfield networks. Okay. And that kind of led to another kind of winter period, right?
Yeah.
When there wasn't that much data, there wasn't an internet and stuff like that. So
yeah, that's right.
It took a long time to come around again. But anyway, if anybody has any questions about these phasers, I mean, these phasers, just to put it in context of Telluride, these phasers were the subject of at least a large part of a topic area group the last couple of years. And I remember Paxson, I don't know if Paxson is there, but Paxson came and he led, you know, he taught a nice tutorial on phasers and involved quite a few people, maybe about 10 people at the workshop and working on these phasers at the workshop. I don't know what the outcome was, you know, of that, but it's still definitely related to the things that Emre was just saying about the fact that spiking networks, there's no point in making just classifiers out of spiking networks. You need to do dynamics with them.
Right.
Otherwise, what's the point of having the time there? So so does anybody have questions?
I have a question, Toby.
Yeah.
Fritz, your talk is probably the one most sensitive to the issue of time. And since you implemented this on Loihi, for example, I'm wondering what you found to be the resolution in time that you need to make this kind of dynamics work.
Yeah, that's a good question. So it really depends on how you implement these, for example, resonate and fire neurons. And so first we just use kind of Euler methods to simulate this in discrete time. And then actually you need quite a lot of time steps per cycle. And if you go to a higher order method like Runge-Kutta, you can actually get away with way less time steps. So I would say that this is definitely something to keep in mind, because that in essence then discretizes your phasal states, the time. And what is very important then is that you actually implement for the neurons internally exact ways how they actually approximate the continuous time dynamics of a resonating fire.
Well, for those of us who are trying to build hardware that can support this kind of model, do you have a rule of thumb like millisecond resolution, tens of microseconds resolution?
Well, it's more how many time steps per cycle, and I would say reasonable numbers are more than 20 to 50, something like that, rather than absolute times. Of course, then I mean, yeah, you can only do so much in one cycle of these phasal networks, and then you might talk about these absolute times.
Okay, thank you.
May I just barge in with a question?
Please.
Yes, please.
Okay, also ich bin jetzt gerade in Tübingen und jetzt täte mir doch wundern, wie das geht, wenn ich bloß eine Handvoll von Transistoren habe und ein Brettboard, ob ich da irgendwie mit 12 Transistoren so ein Ding bauen könnte, das irgendwie dein Modell nachmacht. Now in English again. So I'm calling from Tübingen with a very peculiar dialect, and I was wondering, since I'm not at UCSD right now, is there a way to take a dozen transistors maybe and a handful of resistors and a breadboard and some wires and build one of these phasers just on a breadboard?
Yeah, I'm actually answering in your dialect. People always tell me that I have a Swabian dialect, even in English. So yeah, well, the problem is really the connectivity, and this is the reason why we really are so excited about low-E implementations. I mean, you could, of course, you could build something. You could build an analog circuits that do something like one resonate and fire neuron. But to do something interesting, you need to scale this up to many, and they need to interact with each other by plastic synapses somehow, and this is where your breadboard and the handful of transistors fall short. And at the same time, this is really also, if you compare actually now neuromorphic approaches in terms of scalability to approaches that really implement coupled oscillator models with other technologies, you realize that we are really ahead. So you can do something now with some of the recent neuromorphic hardware that you cannot do with other implementations of coupled phasal networks. And that's really very, very interesting and important that neuromorphic is taking their lead, because the scalability of most other coupled oscillator hardware approaches is, to my knowledge, is quite limited. So they are happy if they can implement 50 coupled oscillators, and that's just not enough to do some interesting computations.
So ballpark figure, how many oscillators would be needed?
Well, I mean, you need thousands. I mean, with on Loihi, we are phasing still in scaling up to hundreds of thousands or 10,000. We are still phasing, but we can do thousands right now. But I think that's the lower limit, that it makes sense to look into it. I mean, yeah.
Okay, now vielen Dank aus Tübingen.
Well,
Okay. All right.
yeah.
Sorry, there's a question on Slack. For the oscillate and fire network, I recall seeing the equation for the neuron update, but can you elaborate on how the input values are fed into this equation and what form should they be in? Spikes, binary values, real values, etc.
Let me see. Can you elaborate input values into the equation? So what equation? So
oscillate and fire. Did you have an oscillate and fire network?
So yeah, let me just go to the standard resonate and fire network here. Let's go to this here. Yeah, so here the inputs are fed in by spikes, and the spikes are then actually weighted and phase turned by still complex synapses. That's kind of the most basic formulation of the resonating fire. So you have an internal dynamic, which is just this decaying harmonic oscillator, and what you feed in is basically spikes, but the spikes can be phase twisted and weighted. So this is, and then of course, this is not something that we implement. We then actually translate these complex synaptic weights into delay weights. This happens here. And then we end up with an equation which is actually just one-dimensional and feeds in spikes through a convolutional filter. So these are presynaptic spikes, and the synaptic filter is this one-sided decaying cosine function. That's one way how you can formulate the dynamics, which is then equivalent to the resonating fire. And then the question is, how can you actually implement these kernels? And this is then so one way to do that is then to use inhibitory pools of neurons that then get you such a wiggly postsynaptic potential. Does this answer the question?
Actually, I was curious, how do you get this inhibitory, how do you get this cosine-like signals out of the
Yeah, there's kind of a membrane integration going on. So it's basically this this plus this.
Oh, I see. Okay.
So an integrator.
Okay, so it's not like a true cosine function, yeah. And so how much does that affect the outcome?
Very much. I mean, if you look here on the lower right, this picture also here we really maxed it out in terms of how many patterns can you store. So this is kind of the similarity of the retrieved pattern as a function of the number of stored patterns. And then you can really see that we trace the ideal non-spiking phasor theory curves pretty well. So we don't lose very much. Also, you can see this is really not, it's really not exact.
Okay, so the weights being complex, is that part of the mathematical definition or the for the model?
Yeah, so I mean, in order to get these limit cycles, I mean, the attractors in the phasor network are of course fixed points, right? There are phase patterns, fixed phase patterns. But if you translate then the phases into spike times, then the fixed points in the attractor model correspond to limit cycles in the spiking neural networks, as you can see here. So you have these neurons that fire periodically. Some are silent, some fire periodically. And the phase offsets between the neurons, they are really, they are governed by the synaptic weights, and the kind of the phase offset patterns really correspond to the stored patterns in these networks. But these are now dynamic limit cycles. In order to get those, you need, well, I shouldn't, so let me back off here. So if you can do a lot just with real valued synapses, and this is actually done in all these Kuramoto models. In the Kuramoto model is a phasor model with real valued synapses. But all you see there is this is this locking between different subsets of oscillators. You can't really have fixed points in the Kuramoto model where you have these offsets between different neurons in the limit cycle. For this, you need a Hermitian matrix that corresponds to a really complex matrix or to a delay.
Okay, I see. And so basically you're saying that you could get this complex weights by assuming there's a delay, right?
Exactly.
This is how it's expressed by the delay.
Exactly. You can basically replace the complex weights, the complex synapses. They basically just determine in what direction here your perturbation from the presynaptic spike is integrated, right? And this can always, you can always wait until the internal state is actually here in parallel with the V, with the V dimension, for example, and then do something which is real valued.
Okay, I see. Oh, nice. That's nice. Are there any other questions from anyone out there? I think there's something on the chat. Let me see.
Yeah, there's a question on the chat.
Oh, no, I think that was from Matthew who had asked the question before.
No, Hector is asking a question.
Hector, do you see it? Where?
Well, how do you physically interpret the complex numbers? Well, yeah, so I talked a little bit about the synapses. And again, we interpret the complex numbers basically by replacing the complex numbers in the synaptic weights by delays. But of course, there's now these two different implementations of the phasor networks. One uses the resonate and fire internal dynamics. And so there you really need a two-dimensional internal state of the neuron. And yeah, one could argue now what that could correspond in a real neuron to, and that's not so. So I don't know. That is up for discussion. And the more biophysically plausible implementation is one where you really go to a one-dimensional equation, to this equation, and you implement. You have then still a postsynaptic potential, which is elicited by each spike, that needs to wiggle with the cosine, and then you can implement that with approximately with pools of inhibitory neurons. And that is approximate, but it's the more biophysically, it's the more straightforward biophysical interpretation of this entire thing. And then basically all the complex numbers are gone. Does this answer the question? Okay. Emre asked, the Kuromoto model and its variants are generally analyzed in the weakly coupled regime. Yeah. Yes. So in the Kuromoto model, you have only these. You have phase-phase interactions. We still have phase-phase interactions, but there is now. There is also amplitude modulation, which is in the simplest case, just binary, 1 or 0. And this allows you to actually express sparse phasor patterns in these DPAM networks. But yes, the interactions are still phase-phase and not, phase amplitude. And I mean, there are phase amplitude too through the threshold mechanism. And there are, of course, also amplitude phase, because only the guys who have amplitude. So in a way, our model already implements now virtual interactions between the phasors. But in the equations, it still looks, so if you go to the Lyapunov function here, let me show that. So since the amplitudes of the phasors are only 1 or 0, we still have, for the guys where they are 1, it's just a phase-phase interaction. But because they can be also 0, it's a little bit more complicated if you talk in general about all the interactions in the network. So basically this model already gives up the strict phase-phase coupling only view. Does this answer your question, Emma?
Yes, thank you.
I think there was one question before that
yeah.
You comment on the specific role, right, of the phase. You see that one? Yeah, Chris is hovering over it.
And could you please comment on the specific role of the phase versus the spatial activation in the place cells? Yes. Yeah, so through this circular convolution exponentiation trick, So basically, vector symbolic architectures usually rest on the premise that every object is encoded by a pattern which is random and pseudo-orthogonal on the other patterns, right? And that's great and works for symbolic processing, wonderful. But what if you want to represent a 2D plane where the rat moves, right? What do you do? And one solution is this exponentiation trick. And so that means now if you move just a little bit on the 2D plane, you generate a pattern which still looks random, but it has more overlap than random. It's not pseudo-orthogonal to the previous pattern. So in other words, you can now define a topology which is also reflected by the similarity of the code vectors that you use for these 2 points, if they are very close. And this is what you do in this exponentiation trick. And that means now that 2 points on the plane that are very close to each other, they have still the same set of neurons on, the same set of place cells, but the spikes are phase processed already. That's the phases of the spikes have already turned, and you kind of get this super resolution by looking not only on the set of active cells when the animal is in a certain location, but also on their phase angles. This gives you super resolution.
I don't see any other questions, so maybe, is there any? Because in the interest of time, maybe we should wrap up.
Shichi, yeah, I think we should wrap it up right now because we're already going 3 hours and we only promised 2 hours. And so can we just show a preview of tomorrow to conclude?
Let's
The program for tomorrow. And this is an important program because it's also the program where we introduce the challenges for the rest of the month. So it's the real work of the workshop besides the work of listening to the talks and learning new stuff.
you have to wait a second. I have to find it. I think yeah. Here we go. Wait, am I sharing the right thing?
Yeah, you're showing it, but you need to show the program. Just show the program page.
Oh, okay.
Have it there. Go down.
Okay.
So tomorrow, right, we have, was it by Cornelia and Andreas? We have actually 2 longer talks, one from Chen Wang at Cerebrus on wafer scale neural computation. I'm sure that'll be quite interesting to a lot of the Silicon Valley people. And the second one is from Mike Davis. Also, I'm not if Garrick is involved in that, but it's about, it's trying to take really low EHE and doing something with it and the next generation low EHE. And then we'll have a recorded talk from Greg Cohen, the recipient of the Misha Mahal Prize. Actually, that'll be at 4 a.m. for him. So he promises a 12-minute, recorded talk. And then he's going to try to wake up and answer any questions you might have. And then we'll have a very important session on the challenges that are coming up starting, I guess, next week. We don't have these meetings scheduled, but next week we're going to start working. And if you're interested at all in these challenges and you've looked at the challenge pages, then join the Slack channels for those challenges and fill out answer the questions that the organizers have for those. And after that, I'll take questions about event camera, Silicon Retina, stuff like that. So that'll wrap up this phase of the workshop, and then the workshop will just keep going. We haven't decided yet as organizers whether we're going to have a weekly or daily meeting somehow for the entire workshop. We have to discuss this, but that's when the real work starts. As if we were in Telluride and like just slaving night and day and partying and working and all that kind of Telluride stuff. So yeah.
All right. Okay. All right. Thanks everybody for attending today, and we'll see you tomorrow.
Bye-bye.
Bye, guys.
Yeah, bye-bye.
Bye. Thanks, Fritz.